I'm Bob Wise. I'm the GM for Kubernetes on AWS. And with me today on stage is a special treat, which is you're getting a couple of engineers from the Amazon.com team. So for those of you who may not be familiar with this, at AWS, we view Amazon.com as a customer, and we treat them as a customer. So even though we all work for Jeff, really what you're seeing here is a vendor with one of his customers here to talk about their experiences using EKS. So really my job here is to try to make sure you get the most out of what these guys are going to talk about. And I want to start that by talking about motivations for what you're going to hear. So although a lot of the talk you're going to hear and see is about kind of technical things, tooling, there's a fundamental business motivator for why it is that teams use these kinds of approaches. And these approaches have come from, at this point, decades of experience in our industry with good intentions, great teams, not actually leading to the business result that you want. And if you start with that great baseline, but then the process and the way the organization works is based on trying to do a big thing, and then trying to get that into production, and then having problems, and then realizing that, oh, well, what we need to do is we need to put some more checks. We need to add more people to the process. Then what happens is you slow down, and because you slow down, you now have to do more. So the lump of stuff you have to get done is now bigger, and that means there's even more stuff that has to be checked. And so you end up in this kind of downward cycle of going slower and slower. And so what has happened is people have realized that you have to take a completely different approach. And if you take a different approach, then you can get much, much better results. So the core of the better approach here is doing smaller things and using automation. So CI, CD are part of that approach. I would say CI has been something that most teams have figured out, but CD, continuous deployment, is really the key to going faster here. And so if you can get to this mode of doing small things, doing them with automation, and doing them with high confidence, then you can get results that look like this. So this is from the State of DevOps report that Puppet Labs puts out. They focus on different things. This is, by the way, all these reports are great. I would recommend them. This was one of the reports that they focused on this area of how do high-performance teams work when it comes to continuous deployment. And you can see these numbers are pretty amazing. And we see anecdotally our customers that adopt this kind of approach see these kinds of results. And so what you're going to see from the team that's going to follow me here in a moment is what that looks like, which makes it especially awesome. They're going to talk also a lot about microservices. I would say as you're listening to their chat about microservices, bear in mind that microservices is a technical thing, and we're going to talk about some technically oriented things around microservices, but remember, it's an org pattern as well, maybe even more fundamentally an org pattern. But to try to help you understand and enjoy the following presentation, I did want to spend a couple of minutes talking about Kubernetes and pods and some basic concepts so that you have a baseline for understanding what's going on. Okay, so Kubernetes. Kubernetes is a operations robot. In fact, the design of it is very, very much a robotics design. And so what you do is you have a bunch of hosts, you need to run a bunch of stuff, put those things in containers, and you tell the robot, hey, I think I need 3 of these running at all times. So we let Kubernetes, the way we define that is with this thing called a replication set. We ask Kubernetes to please take care of this, and it will go and do it. And you don't actually tell it put 1 on host 1, 1 on host 2, 1 on host 3. It goes and figures that out based on a declarative state. Please go do this. Now, I do have a picture here showing a human being doing this. Not recommended. This is by way of example. This should ordinarily be done through pipeline automation, which is another form of robot. So we have sets of robots all doing different things. But this is the result you would get if you went and played with Kubernetes command line directly. OK, so I've realized now I need more containers. I'm doing horizontal scaling. So I might say, please change that number to 5. Please make sure there's 5 running for me. And Kubernetes will go and do that too. So it's providing a scheduling and placement capability here. So this is where you get to that more kind of declarative approach, and why this is not just a scheduling system, but more of a complete lifecycle system for managing containers. So I've asked the system, I've asked our robot here, please make sure there's 5 of these things running, and one of our hosts died. So Kubernetes says, oh, the state of the system is not what it should be. I have to fix it. And it will go and schedule those as best it can. So this helps quite a lot. If you're automating operations in cases like this, you might not even have your pagers go off. This might be something you deal with the next day instead of in the middle of the night. That's just a flavor for what Kubernetes does. There's all kinds of other things you need to do with real applications. For example, a human being changing the numbers from 3 to 5 based on load probably isn't what you want to do. You have metrics that feed into that. So you say, please make sure the load on the system always is at least X. You feed metrics in. The system itself will update that. Within Kubernetes, that system is called HPA. Also, you need to do things like route traffic. You need to manage the deployments. When I say manage deployments, this is pipeline concepts. I have to go from version 1 to version 2 and do that in some sane way. I also might have constraints around running multiple containers together on the same host for, let's say they have a shared memory queue. So in Kubernetes, a pod is the concept used to encapsulate multiple containers that have to run together. They share an IP address. They share a security context. They can share storage volumes. That's called a pod. You're going to see a lot about pods here coming up. You also don't want to have clients of that system worrying about how many pods they're running at any time. Maybe there's 3, maybe there's 5, maybe there's 100. So you need to be able to do load balancing across those. So a service is the concept in Kubernetes used to do this. It has an IP address. It manages the IP mapping of the service to the IP addresses in the pods, which may be shifting around underneath. And deployments are a really cool thing. So if you think about what you would want to do when you do a rolling deployment, you have 3 pods. They're all at version 1. You want them to go to version 2. You probably don't want to throw them all away and then deploy the new thing. You probably want a system that's going to do something snazzy like start to deploy version 2 while version 1 is still around. Do load balancing across that set. Make sure that the new thing that rolled out is actually working. If it's failing its health checks, you probably want to roll it back, which Kubernetes will do for you. Or if things are working pretty well, everything's passing its checks, you can start to roll those out automatically. And Kubernetes has a lot of knobs and dials to let you tune exactly what the policies are for this kind of deployment. So that's just a quick snapshot of the kinds of things Kubernetes does. All of that robotics infrastructure running needs a bunch of stuff like shared cluster state. Kubernetes uses a system called etcd. You'll hear in the following session here a lot of talk about etcd. etcd is a distributed Raft-based consensus database, a bit complicated to manage. Troubleshooting it can be tricky. This is part of what EKS does. So the EKS service is Kubernetes run in a distributed, highly available fashion with all kinds of monitoring and repair and the EKS team standing behind it. So we run upstream standard Kubernetes on your behalf, or in this case, on the behalf of the Amazon.com team. So production grade, HA, highly secure. we run upstream, so it's just like the Kubernetes you would run yourself, but we take care of that undifferentiated heavy lifting. Also, the EKS team contributes to the Kubernetes project upstream, and especially to a lot of the integrations between Kubernetes and the rest of AWS through integrations with networking and storage and so forth. So we're very committed to not just supporting EKS, but also supporting all the other ways you can run Kubernetes on AWS. More Kubernetes is run on AWS than anywhere else. A lot of Kubernetes running on AWS. There are a number of options to do that. Many of them do some flavor of build that slide that I showed you a minute ago, building and installing etcd and the other control plane pieces and trying to manage those for you. But you're really on your own. If you have a problem with troubleshooting etcd, where do you go? You have to have those skills yourself. So there are a number of open source software systems designed to provide that kind of tooling. kubeadm, kubeAWS. One of the more popular ones is a system called COPS. You're going to hear some discussion about COPS here as well. Many commercially supported partner options as well. And I would say you can also do some mixing and matching. We have customers who use COPS, but then use the CNI drivers that the EKS team builds. So with that, I'll hand it off. Kevin?
Yeah, thank you very much, Bob. Thank you, everyone, for attending today. So my name is Kevin Delane, and I'm a senior software engineer for Amazon. And Christian and I both work for the Amazon Shopping Foundations organization. And Shopping Foundations builds the foundational software upon which we build shopping experiences. And you're probably familiar with many of the shopping experiences we have, such as the Amazon homepage, where you can start your shopping journey. There's the search experience, where you can enter some key terms and find a list of products you might be interested in. You can go to the product detail page, where you can drill down into additional details about a product you might be excited about. And then finally, the checkout experience, where you can complete your shopping journey, purchase your products, and get them shipped to your home. And so Amazon Shopping Foundations is building a new managed internal offering to improve how we build shopping experiences. So within this section, we'll talk a little bit about Amazon's path, a little bit of the history around moving from a monolithic architecture to a microservices architecture, and also like why we think moving shopping experiences to a microservices architecture is the right decision. As well, we'll talk about some of the requirements we had as we were looking at how to host the execution of these microservices. And so something that's important to understand is the concept we have internally of a two-pizza team. It's how we organize our development teams. 2 pizzas should be roughly enough to feed your entire development team, which ends up being about 8 to 10 developers. It encourages the teams to be autonomous, so they should be able to make decisions on their own and try new things out, as well as agility, so they can try new things out very rapidly, gather data, and decide if they made the right decision. Something else to understand is in 2002, there was a mandate that teams should communicate across network-separated APIs. Amazon didn't always have a distributed architecture, and so the original Amazon.com website was actually deployed as a single binary. Developers are clever and found ways to enable communication across different parts of the application, but this caused a lot of coupling and made it very hard to evolve the application over time. And so the mandate in 2002 dawned the era of service-oriented architectures within Amazon. We use APIs as a mean of communication across teams directly. Service-oriented architectures are generally focused on data-oriented services, ones with very structured input and output. But shopping experiences are built on top of rendering services, which the input may be structured, but the output is generally generally HTML. And so as part of building towards this microservices architecture, we're trying to improve some of the framework support for adding some of the more structured input and output around rendering services. And so like I said, shopping experiences are built using rendering services. Within Amazon, we refer to these as page applications. And a page application includes both the business logic and the templates required to render a shopping experience. Page applications are owned by the team who own the shopping experience and are generally optimized for that shopping experience. And each of the team establishes its best practices through the structure of the page application. And so, challenges that the Amazon homepage team might face are very different than those that the checkout team faces. And their page applications will represent that with how they serve requests and structure their code. And so while shopping experiences are owned by a single team, the features that get contributed to that shopping experience are themselves also owned by a variety of teams across Amazon. And the way that most teams will contribute features to the page applications is by committing that code to the same code base as the page application. And this results in teams building features that are very much optimized for the shopping experience for the page application that they're being committed to. And ultimately, this leads to feature changes being released in the same CI/CD pipeline. And so in general, CI/CD pipelines should improve the velocity at which you can release changes. But when all of these teams are committing the same code, what we actually find is the velocity can go down over time. And so the pipeline release process, again, intended to increase velocity, becomes a bottleneck. In turn, this increases the operational burden for the teams who own these page applications. The page applications become monoliths in their own right. And monoliths are very difficult to maintain over time. They become more and more complex as you add more and more code, which makes a lot of sense. And so the idea that Amazon Shopping Foundations had was let's decompose the shopping experience. Let's break apart these features into a microservices architecture. And so there's a number of approaches, or there's a number of benefits that we see with this approach. It provides feature teams and these page application teams independent release cycles. It eliminates the pipeline as a bottleneck to releasing new features and to updating existing features. And decoupling feature releases allows the teams that own the features a much more rapid experimentation cycle. It also lowers the friction for creating new features. And so there are teams who might want to experiment with a radically new experience or a radically new feature. But if they have to contribute that code to one of these page applications, they may be less likely to do it because the cost is much higher. And so in this microservices architecture, we believe that the cost will be much, much lower for these types of experiments. But one of the biggest benefits we see with microservices architectures is that we can isolate feature execution from each other. And so if feature A starts failing during execution, feature B won't be impacted. And ultimately, the entire experience that we serve to our customer should not be impacted either. We just won't be able to show that one feature. And so the way that teams contribute features in this architecture is just by building a new front-end microservice. Hosting of the microservices is owned by the managed services team. So this allows the feature teams to focus on delivering business value for Amazon, but really more importantly, it allows them to focus on the functionality that delights Amazon customers. The managed services team takes on the responsibility of scaling and of providing the availability promises that feature owners expect. Shopping experiences teams manage which feature will actually end up in their shopping experience. And so what happens here is rather than deciding what features are going to go into a specific experience being a very technical decision, we're able to turn that into a business decision so these teams can have a conversation about, hey, do we think this is the right experience for our customers? So as we started this project, we started this program, one of the things we wanted to avoid was big bang migrations. Big bang migrations can be very costly. I'm sure you're aware of that. And then they also greatly increase the risk of success of the project. And so one of our core requirements was that we wanted teams to be able to incrementally adopt this architecture. And what we've done is enable teams to integrate these microservice-based features next to legacy features within the same experience. And we see as the number of features being built in this architecture grows, the role of the monolithic page applications will get smaller and smaller over time. And we expect that the shopping experiences will be completely composed of these microservices. And so actually today we are serving the majority of the features on the Amazon homepage using this microservices architecture. And we are continuing to expand the footprint of features being served in this architecture over time. So before we go on to the next section, I did want to talk a little bit about how we thought about the requirements as we were building out the hosted execution environment. High availability is a core requirement for any service being built at Amazon. Outages happen, but our services need to remain redundant in spite of failures. Scalability, though, is just as important. So we want the ability to scale our system, our managed service, out over time as we grow the number of customers, and the set of use cases that we can support also increases. But reliability is just as important for us. We need the system to work as expected and to be predictable. No one likes to get paged at 2 a.m., and if we can reduce the amount of times that happens, that's great for us. So based on those requirements, we made some key decisions. So we package our microservices as Docker containers, as Docker images, and we run them inside of a Kubernetes cluster. And we're currently using Amazon EKS to execute all of these microservices. But we didn't always use the EKS. And before it was available, we actually used, as Bob said, the COPS command line tool to create our clusters. And we launched our first experimental cluster in December of 2017. This cluster was managed and continues to be managed by a 2-pizza team, 8 to 10 developers, and none of the team had DevOps experience when we started. So given the team size and the scope of ownership of a Kubernetes cluster, there was a lot of risk to the success of our program, in owning this cluster. And early on, we did some very hacky things in order to try and stabilize our Kubernetes cluster. Right ahead of our launch, we ended up with a very unstable cluster, which was not ideal. And so in this section, we'll talk a little bit more about how moving from our COPS-based clusters to managed clusters through EKS really improved our ownership, our ability to serve our customers by being able to shift some of our ownership over to the EKS through their managed service. We'll talk about some of the problems that we were facing that when we made the switch just were eliminated for us, which was great, and how we see using EKS as the ability to drive some more value to our customers. So our cluster, again, became unhealthy right ahead of our experimental launch. Luckily for us, we had been in discussions already with the EKS team. When they launched their preview, we very quickly started looking at how we might migrate our build logic, and around that same time, our cluster became completely unusable. Luckily, the changes required for us moving from COPS to the programmatic APIs through their AWS was very minor. There were some small component changes in our cluster that had to we had to move around, but ultimately it was a very quick transition. And throughout this section, we'll talk about a little bit more where making this move solved those problems that we were facing. So the first big one was we did not have a strategy with our COPS-based clusters around how to manage in-place updates to the cluster. Christian will talk a little bit more about this later, but we did the way that we actually performed updates was to migrate our workloads from the cluster that we were running in production to a brand new cluster where the updates were applied. That's fine, but it's a very heavyweight process. We've improved that over time, but it's still not our first choice for how to apply updates to the cluster. And so when we were talking with the EKS team, they discussed the fact that, well, we can manage the updates to the core components of the cluster, like the control plane, on your behalf. And so after we made the switch, we were actually really surprised the first time when we found out that a security patch was applied to the cluster, and we had no knowledge of it. And in fact, there was no impact to our online traffic, and it was just it was something that we followed up with them to learn more about. But it's great because this is also true for more regular software updates. Will just be applied to our cluster, and we don't have to worry too much about it. It provided us with a lot of confidence, both in Kubernetes but EKS as well. We can stay up to date with security patches and not have to be focused on that from our team. And this really reduced the cognitive load on our team. We had a lot of other areas to worry about, and this just became one that we didn't have to. Another area that moving to EKS really helped us out with was etcd management. And as Bob talked about, it's the underlying data store for the Kubernetes control plane. It's one of the most complicated components in a Kubernetes cluster, and it really requires deep knowledge to operate it efficiently. And due to issues with how etcd provides its consistency guarantees, it's possible for it to get into an inconsistent state, and it causes problems with consistency. I'm not going to get into too much into how it provides its consistency guarantees, but basically there's a leader election policy where a protocol where one of the nodes becomes the leader and manages the relationship with the client, and that state is replicated out. There are edge cases where we can end up in this place where the cluster becomes in an inconsistent state. And so due to our hacky upgrade process, and we were actually using an older version of etcd than would be used now, our alpha cluster, this experimental cluster, got into a really bad state. The symptoms seemed to indicate that one of the nodes gotten into this inconsistent state, and it couldn't recover on its own. In general, actually, that's OK, but you need to have the process in order to recover it back into a healthy state. Our team's lack of depth in this area put us in a bad position because we just didn't have a plan for how to recover it. And so moving to EKS has actually eliminated this area of ownership for us altogether. The EKS team will manage the etcd cluster, monitor it, and make sure that it remains in this healthy state. Something to note, though, is a newer version of etcd, the one that you would be using, is not as prone to this type of error, and so it's unlikely to occur again. And one other area where moving to EKS really helped us out was around scaling of our masters. And so when we created the default setup for a COPS-based cluster is to put your Kubernetes control plane and the etcd nodes on the same host. And so this couples the scaling of the control plane to your data store. And so in our cluster, we have a very chatty component. And it turned out it was actually causing the control plane to brown out while we were serving online traffic, which is just not an ideal scenario. We couldn't make changes to the cluster. And so our hypothesis is actually that this contributed to etcd becoming unhealthy because it ran on the same host, and it was driving very high CPU utilization. And we think that they were unable to talk to each other, the etcd nodes. We didn't actually follow up on this because we actually moved directly to EKS, and it solved this problem for us altogether. Scaling of the Kubernetes control plane was separated from scaling of the etcd nodes, and we just didn't see these brownouts anymore. We still run this very chatty component, and the master nodes, the control plane, just scales up and down automatically for us. We've actually improved some of our own management of the cluster, and I'm sure that's helped. The point here is that we actually don't think about this problem anymore, and we'd prefer not to. And it's great that the EKS team can take care of this for us. And so EKS has really helped free our team up from having to gain deep knowledge in areas that don't directly contribute to the success of our customers, that doesn't bring additional value to the customers that we serve. And while all of them are immensely valuable, it's worthwhile for us to delegate that ownership to the EKS team. It allows us to focus on delivering this microservices architecture to our customers, to focus on solving the problems that they want us to solve, and delegate the rest to the EKS folks. And so through this next section, we're going to dive deeper into how we've actually, or Christian will dive deeper into how we've actually utilized EKS and containerized applications to address the needs of our customers.
Thank you, Kevin. Hi, everyone. My name is Christian. I'm a senior software engineer at Amazon. So Kevin talked about how we plan to break apart the shopping experience and the features running in it into multiple microservices. So in the next slides, I will walk you through how we built a private managed offering to enable our customers to do so. And we'll finish up by showing how we did a live migration of a cluster in production. So we did this based on 3 principles. The first one is, as Kevin already mentioned, we wanted each feature to be an independent containerized applications that we will deploy as a microservices inside the cluster. And we wanted to expose these services as endpoints to page applications to consume. This enables decoupling between the features as well as the page applications. We also wanted to provide gradual deployments for our customers to minimize the impact in case they deploy buggy versions of their code. So what we wanted to do is every time they deployed a new version, we wanted to slowly shift traffic from the stable version to the newer one, reducing the impact on customers, if any. So we can either roll back the deployment to the stable version or continue deploying until we replace to the new version. And the third one is that we wanted to provide highly available elasticity for our customers so they can focus on developing features and not maintaining infrastructure. This particular constraint have two major requirements. The one, our solution had to be able to support Amazon retail traffic, which is by nature high in volume and has unexpected spikes of traffic on any given day. And we also needed to support special days with special kind of traffic, like Prime Day or recently Cyber Monday, for example. The second requirement was that the SLAs of these services had to be super, super fast. All of these microservices are directly rendering content to the page, so any added latency that way these services may add could impact directly Amazon customers viewing any shopping experience. So we came up with this high-level architecture that I will be talking about during this session. What our customers mainly see is their pipeline and nothing else. Everything is abstracted for them. And that pipeline is directly integrated with our control plane. Our control plane, what it does is basically manage two types of resources. One, of course, the microservices running inside the cluster, which we configure to auto-scale and publish metrics to CloudWatch, et cetera. And the second resource we manage is a Route 53 entry, Route 53 domain, in which we expose the services that are running in the cluster that eventually resolve to those services through a private link that we expose to page applications. So the first thing we do is deploy these microservices, and we deploy them with what is called a cluster IP. The service on the cluster IP are just construct from Kubernetes. They don't actually allocate any computing or networking resources until actually pods are allocated to that service. So when this happens, we use a plugin that is called Amazon VPC CNI K8 plugin that is basically responsible for assigning a unique IP to each of the pods running in the cluster, so making each pod addressable within that network. Second, what we do is we deploy an ingress controller, which is another name for a software load balancer, basically. This component is responsible for routing the traffic within the cluster to any of the services that we are hosting. The difference between the ingress controller and the services is that the ingress controller we deploy it as a node port. So instead of assigning a unique IP to each of these controllers, what we do is deploy that component on every node, listening on a specific port in that node. So for example, in this case, the ingress controller will be listening on every worker node on port 5000. Now to expose our software load balancer to external traffic, what we use is a network load balancer. We chose an NLB mainly because the high volume traffic we need to serve and some requirements we have had around TLS. But there is a blog out there on AWS that compares ALB and NLB, and you compare to your use case. So finally, what we do is expose the software load balancer through a private link to customers running on other VPCs external than ours. And when we do that, what we do is that for each service that we host, we create an entry in Route 53 that basically resolves to that same VPC endpoint that goes through the private link. So all of the services will be pointing to that same IP address that is resolvable only on the page applications VPC. Then when requests come into our cluster, it is routed to any of the software load balancers. And what we do is we use host header routes to route the traffic to a corresponding service. So for example, if we see a request with full feature in the host header, then we will route it to full service. Similarly, what we use for gradual deployments, our second biggest requirement, is we use weighted routes inside the server, inside the cluster, to shift the traffic in case of new deployments. So whenever a new deployment for a service comes around, we deploy the new pod, and we shift the traffic between the two versions. We don't do canary releases, which is basically you shift traffic to a certain threshold and then go to 100%. What we actually do is incrementally shift traffic over time until we reach 100% to reduce risk. And as we deploy, what we do is measure metrics that are coming outside of the applications. The way we collect metrics is that we have another container running in the pod of the service. Remember that a pod is just a representation of your logical host, but may have one or more containers. So this specific container is responsible of collecting metrics about your requests and responses, as well as other metrics that the application may choose to publish. And what we use is Prometheus to collect these metrics out of the services into a time series database. So basically, we aggregate in two spots. The first one is at the pod level, the second one on Prometheus, and then a third time on a custom solution that we built for this cluster to aggregate a third time, and publish those metrics to CloudWatch. With this, we reduce the number of entries or metrics we need to publish to CloudWatch without losing the data that we need to monitor. And finally, for highly available elasticity, we use two components. The first one is HPA, or horizontal pod autoscaler, which is a control loop that runs inside Kubernetes by default every 15 seconds, but you can adjust it as you see fit. And what this component does is it monitors the mean of a given resource at the pod level and compare it to the target that you want to set to monitor. For example, if you set the target to HPA to be 50% usage of CPU, what this component will do is take the mean utilization of CPU among your services, and if the mean utilization is too high, then it will create more pods to lower that value to the desired threshold. And same thing other way around, if it is too low, it'll decrease the number of pods. And the second component is the cluster autoscaler, which is responsible for adding more node in your autoscaling group when Kubernetes needs more space to create more pods. The other way that this component works as well is to optimize your usage. So if there's an opportunity to redistribute the pods and assign them to existing nodes to free up space, it'll also do that. So with this architecture in mind, what we set up is we decided to take baby steps to prove our architecture. So we addressed first the problems of running the services, exposing them on endpoints, and be able to actually gradually deploy to prove first our architecture. And we decided to do later the highly available elasticity. So we went to production in a closed beta project with our partners. And what we have observed from almost day one is that we were able to meet the requirements for our SLAs. So services were running within SLA, and the latency added by the network diagram that I just showed you was very low. So we measured that the request response time was 4 to 5 milliseconds at P90, which could basically be ignored compared to the benefits that we were getting out of this architecture. And it was not impacting actual customers viewing pages on Amazon homepage at the time. But what we did observe was every time we made any change on the scaling of pods or nodes in the cluster or any configuration change that would cause pods to be created or deleted, we will see a drop on availability on these services. So we dive deep on this problem, And what we found was that the cold start behavior of our applications and the runtime we provided for our customers was really, really slow. So every time we created a new pod, it'll take 1 to 2 seconds for the application to be warm enough to serve traffic at the SLAs that we needed to. After those 2 seconds, the pod will be on a normal state and we'll be able to serve as the measures that we see at P90. So we decided to actually invest in our runtime and get it to a point in which it could almost start instantly. After we deployed that, we measure again, and we saw that all of the errors were gone. So we were pretty happy with it, and that let us focus on how we could configure elasticity, and how can we use this information to do so. So we basically came to the conclusion that there is a relation between the speed at which we wanted our services to scale and the speed of our SLAs directly related to the threshold we will set to the HPA. So we measure this and put our cluster under load, and what we come out with is that 60% was kind of like the sweet spot for our types of workloads that could meet our requirement of low latency services. Anything higher than that would make our pods too hot and see, again, the same errors. And anything too lower than that would be basically just a waste of resources. So we're happy. We think we made it. And we just started experimenting with this in production and started observing how this behaves. And basically, is it working or is it not working? And what I'm showing you in this graph is our first scaling event on January this year in production, which was a increase in traffic in one of our customers that increased about 8x over a period of 7 to 8 hours. At this time, basically what you can see is that the utilization within the cluster of the services that we were hosting increases basically linearly to that same graph. And what we saw in our HPA is that it needed to increase the utilization, the requested CPU 3 times to cover this traffic. But the actual spectacular part for us on this is that throughout that event, the availability of all of the services stayed steady at 100%, which we were absolutely very happy with. Similarly, for the autoscaler of nodes, we see the same behavior. This dashboard, what I'm showing you, is not actual production data, but is one of the testings that we did in preparation for Prime Day this year. As you can see, the request count also increases. I think in this time is 2x over a period of a couple of hours, and we see exactly the same behavior. Node count goes up until the traffic goes down again, and then we release the nodes again. And then we updated the cluster. As Kevin mentioned before, we started with COBs and without EKS, and this is a story about that era. We haven't seen this problem after we onboarded to EKS. At the time, the problem caused all of our routes to be affected, having a huge impact on the availability of our customers and the services we're hosting. So that was an eye-opener for us. At the time, we had all the levers because we were under experimentation. But that drove a critical decision for us is that we will consider all of our infrastructure ephemeral and the clusters to be immutable. So by this, we mean once we deploy a cluster into production and we host services on it, we don't touch it to avoid introducing errors like the one I just mentioned. And this triggered 2 lines of work in our team. One is we were absolutely focused on automation our infrastructure. And today, we're able to spin up a cluster from scratch by executing a script, and it'll be ready in 15 to 18 minutes. 18 to 20 minutes, ready to serve traffic. And the second important thing is that since our clusters are immutable, we needed a deployment process to update our own changes. And we decided that we wanted the same experience that we were providing to our customer. So we wanted to have gradual rollouts of our cluster changes. And the way we do it is actually pretty much the same way. Every time we need to propagate changes to our infrastructure, we spin up a new cluster with a new configuration and use the same process to migrate the workloads from one cluster to the other. And the only difference here is that instead of using weighted rules on the ingress controller, we use weighted rules on Route 53. So Route 53 in this case is responsible for shifting the traffic of the same service, but across 2 clusters, and then we can compare the performance of those services on different configurations. We do this with every workload, and once we're ready, we let it sit for a while, comparing both metrics, and once we're satisfied with it, we basically just kill the older cluster. Though this is a great feature for cluster rollouts, it enables some other more advanced patterns in our architecture that we're trying out this year, is that we can go and pursue a cell-based architecture for our offering. So if you're not familiar with what cell-based architecture is, it's just basically you don't put all your eggs on the same bucket, and you split them up on buckets of the same size. When you do this in computing, basically you can enable higher testability, as you only need to test one cell to prove your code. You can have higher scalability as if your system grows and your customer grows, you can grow just by adding more cells into your architecture. And more importantly as well, it reduces your blast radius, as if one of the cells becomes unavailable, you just impact a subset of your customers, or maybe none of them, depending on your design. So we're exploring some architectures like this, in which you define a threshold for your cell, and you scale out internally in the cell until you hit the limit, and then add additional customers to the cells you start spinning up as you scale out. When you lose one, then you impact only a subset of your customers. Another option could be you make sure to deploy all of your workloads in 2 or more cells. Then if one cell is impacted, then your customers are not impacted, but you have to make sure that the other cells are available to take this overload until you recover. So what I will show you now is an actual live migration that we did in preparation for Cyber Monday. At the top, you see, these are our actual production dashboards. So at the top, you see the dashboard of the live cluster we have in Europe. And at the bottom, the new cluster we have spin up to migrate and deploy the new configuration. On the left side of the dashboards, you see the availability of our load balancer, the availability of our ingress, and the nodes. At the middle, the values of these metrics. And on the right side, the performance of the services that we are hosting. So at the bottom in blue, you will see the success rate. And on the top in orange, you see the average errors that we see on running in production. But the availability is always stays high above the SLA. You will see the dashboards updating because we compressed this in a couple of seconds, but this was a process that lasted 35 minutes or so to just migrate the workloads, and then we let it sit for around 20 minutes. So if you can see, immediately the request count increases on the new cluster, and slowly the request count and the success request on the live cluster starts going down and down and down as the new one goes up and up. In both cases, the availability of our software load balancer is steady, as well as the availability of our customers. So once that all the traffic is shifted, we let it sit for a while, and once we're finished with it, then we just kill the cluster, and we're done with it. This was live with production traffic. None of our customers were aware of this, and we could do everything behind the scenes. So key takeaways from this session. Ownership is hard. From experience, is very, very hard. And managed services make it easier. We started with this project even before EKS was available. So we have a bunch of legacy components as well in our system, and we're working towards moving to other AWS services like Containerized, App Mesh, etc. If you're using EKS with your own nodes, make sure you manage You monitor your use and reserve resources so you can optimize your configuration over time. And if you're planning to use autoscaling the way similar to how we're using it, we think it's critical for you to understand what is the SLA you want to achieve for your services, and from that you can work backwards to your configuration. So if your SLA hasn't to be as fast as ours, you can allow your services to run hotter because you don't need that speed when you do autoscaling. If you observe any events on Kubernetes of spikes of traffic, don't be alarmed. We've usually observed Kubernetes recover itself with no manual intervention. And we started with very sensitive alarms that basically we just delete over time because they were just noise for us. Last, we recommend to design for ephemeral infrastructure. You don't have to necessarily have a cell-based architecture if you don't want to, but automating your infrastructure will at least allow you to have a fast recovery plan in case of disasters. So thank you so much for joining us. Please remember to fill the survey. We will not be taking questions on stage, but if you have questions, please join us. We'll be happy to answer them. Thank you.